Hi, and welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video 16 in the series, Systems of Equations, Part 2. So in the last video, we looked mostly at a graphical interpretation of systems of linear equations, where finding the solution was equivalent to finding the intersection between two lines. If the lines had different slopes, then there was one point, which was a solution, one point at which the two lines intersected. If they had the same slope, then perhaps they never intersected, in which case there were no solutions, or perhaps they were actually the same line all along, in which case there were perhaps an infinite number of solutions. Any point on the line satisfying one equation satisfied the other. In this video, we're going to focus mostly on algebraic approaches to solving the systems of equations. This will rely on solving equations for a variable, so if you want to go back and review the videos on that subject, that might be appropriate. Essentially, we're going to use substitution to reduce two equations with two variables down to one equation with one variable. And once we have one equation with one variable, we know how to solve that. Let's look at an example in the following system of equations. Y equals 2x minus 1 and y equals negative 3x plus 9. Now, they really are two very separate rules, two separate lines, a yellow one and a blue one. But if we're going to find where they intersect, at that point, the y's and the x's will be the same. And if they really are the same, then these two y's should be equal to each other. And if that's true, then I can replace each y with its rules. This is substitution. Now, I want you to notice what just happened. We went from having two equations, both solved for y. We set them equal to each other because they are both equal to y. And now we just have one equation with one variable, an x. We solve that the way we usually do. Let's bring the 1 over to the other side, and the negative 3x, let's bring that across as well. I really am doing the same thing on both sides here. I just kind of like to do it in one step. If I move my non-x's from left to right, I know I'm going to move my x's from right to left. And once all the dust settles on that, we have 5x equals 10. Dividing by 5, we get x is 2. Now we found out the x value at the intersection point. Once we find that out, we can go to either of the two equations and substitute that value in for x. And when we do that, we get a value for y. In this case, evaluating it out, we get 3. So we have a solution at 2, 3. I just want you to note that it does not matter which one of the two original equations you picked, you should get 3 in either case. And that makes sense. We found this point x by declaring the two y's to be equal to each other. So it would be weird if now we found out they were different. So I want you to write this example down as critical notes. This is a critical example, shall we say. And I've streamlined it without a lot of the commentary. So let's say you wanted to solve this system. You would first, they're each set equal to y, so we could set them equal to each other. And then solving for x, we get x is 2. Plugging in that value of x, we get a value for y. And those two together are a solution to the system. Now I want you to ponder something. I want you to think about this. What about systems that have no solution? What are they going to look like? What will they have in common? Think about it for a moment. Let's scroll down and see if this matches your expectations. Let's take a look at the system, y equals 3x plus 2, y equals 3x minus 1. Notice the matching in the slope parameter. If we try to solve this, we set them equal to each other. And what will we find? Well, minus the 2 over, minus the 2, minus the 3x over, minus the 3x, I get 0 equals minus 3. Well, 0 is not minus 3. That's a contradiction. So what does this mean? Where did we make a mistake? Well, we made a mistake when we set them equal to each other, because actually there is no y such that they will be equal to each other for some value of x. So that was a mistake, but not one that we would have ever seen unless we sort of a priori knew, oh, well, they have same slope, different y-intercepts, so this should have no solution. This is what no solution looks like algebraically, right? No solution, if I solve the system and I find a contradiction, it meant that the original system had no solution. So again, if they have the same slope, different y-intercepts, there will be no solution. And that's what it would be geometrically. Here's what it is algebraically. You find a number equal to some number that it's definitely not equal to, then there's no solution. Let's take a look at another kind of example that we could have, where our system is given in standard form, or something like it, right, where the x's and y's are on the same side. So here I have 3x plus 2y equals 4, 2x minus 2y equals 6. How do I solve this? Well, one strategy we could use is to solve both of them for y. If we solve both of them for y, and here I've done that, well, now we're in the same situation that we were with the first example. We're in y equals mx plus b form with both of them. And since they're both equal to y, we could set the x expressions equal to each other and now solve this equation. So I'd get rid of the fraction first. Let's multiply by the denominator on both sides, and that, once we distribute, will give us an equation that has no fractions in it. Huzzah. And then solving that, let's bring our 6 over here as positive 6. Let's bring minus 3x over here as plus 3x, and we get, again, 5x equals 10 again. Well, that's kind of a coincidence, but it's a nice one. We get x is equal to 2 in this case. And then what will we do to solve? Well, pick any equation you like of the original 2, plug in x, and we get y is equal to minus 1. I want you to notice that I chose one of the equations I'd already solved for y instead of the original one that it was equivalent to, because this one's already solved for y. That just makes our life a little easier. In any case, we wind up with a solution of 2 minus 1. Here's another strategy you can use. That one, by the way, is sufficient. If you want to use that one and drill on it, that's fine. That's a perfectly valid way of doing things, but there are at least 2 more good ones that I'd like to show you. Number 1, you could just solve one of the equations for y and substitute that equation into the other. Here's what I mean. Let's pick one of the equations, like 2x minus 2y equals 6. Solving for y, again, I get y equals x minus 3. Take that expression and plug it back in for the y value in the other equation, 3x plus 2y equals 4. Then I get 3x plus 2 times x minus 3 is equal to 4. Distribute the 2, and I get x equals 2 once I'm done solving. Okay, well, now this is exactly the same as before, and we wind up with a solution of 2 minus 1 again. So this is another way of doing things. I only had to solve, in this version, one of the equations for a variable, and then I plugged it in, and I had something where I had a couple different moves to do, but I got the same equation in the end. And now we have the third strategy. This is perhaps the most elegant strategy. It's called elimination. And it only works if we have a certain kind of setup. If one of our coefficients for one of our variables is the negative of the same variable's coefficient in the other equation, or if we can mess with the equations to make them that way, then we can do this cool trick, which is called Gaussian elimination. Let's see what I mean by having them the same variable have have coefficients which are off by a sign, right? So here we have y's. I have a plus 2y in the first equation and a minus 2y in the second equation. So the y's have the same coefficient, it's just different by a sign. It's different by a positive or negative sign. If that's the case, we can do this cool thing. We can just add the equations to each other. Can we do that? Yeah, totally, because we're doing the same thing on both sides. 2x minus 2y is equal to 6. So if I add 6, or if I add 2x minus 2y, that's the same thing. They're equal to each other after all. So if I add this on the left and I add this on the right, I really have added the same thing on both sides of the first equation. Now, but look what happens if I add these two y terms together. They cancel. That's why we needed them to be off by a sign. And in that case, I get, again, 5x equals 10. We get x equals 2, and we could solve. Here I'll substitute in, I never solved for y, so I'll actually substitute it into one of the original equations. But again, solving for y, we'll get the same answer, minus 1, and that becomes a solution to the system. So Gaussian elimination is the fastest way by far if you're in this ax plus by equals c form, and you notice that you're off by a sign in one term. Now, we can often make that the case by manipulating the equation. Let's try to do that here, although this system of equations might have more than meets the eye to it. So I have 2x plus 3y equals 4, and I have minus 4x minus 6y equals minus 8. If I multiply by 2 on both sides of the top equation, which I'm always allowed to do, I'm always allowed to do the same thing on both sides of an equation, I get a new equation. And this equation has a 4 in the right spot. Now I can add the two equations together. The x's will cancel, but wait a minute, so do the y's, and so do the 8's. Then I get 0 equals 0. Did something go wrong? What does this mean? Well, no, nothing went wrong. This statement, 0 equals 0, is always true, and it's true no matter which x and y you picked. This is what's going to happen if the two equations were actually secretly the same line all along. And in this case, they were. Another way that we could see that is to solve those equations for y. This is that first strategy above. Watch what happens if I do that. So if I bring my 2x over, I bring my 4x over, and I divide off the coefficients, once you reduce your fractions, you get the same equation, y equals minus 2/3 x plus 4/3. So really, these equations were the same all along. The solution is the entire line y equals minus 2x plus 4/3, or sorry, y equals minus 2/3 x plus 4/3, and that has an infinite number of points in it, and ergo an infinite number of solutions to the system of equations. Any that satisfies one will satisfy the other because they're actually the same. So now let's move on to your praxis exercises. I'd like you to, by whatever method you like, solve these three equations, these three systems of equations. You can return to the previous steps in the video, but I want you to really think about it. Try not to rely on previous examples too heavily. You want to try to reason your way through the problem. So pause the video at this time and give that a shot. All right, let's see how you did. So let's look at the first one. The first one I notice is really close to being solved for y in both equations. If I take x plus y is 7, and I minus x to the other side, now I have two equations solved for y. If I want to know where they're equal, I set them equal to each other, and I solve for x. This gives me x is equal to 1. So plugging that back into either one of the equations, I think this is probably the simpler one, I get y is 6, so the solution is 1, 6. The second equation is actually set up to do Gaussian elimination. We have a 3x and a minus 3x. If I add those together, the x's cancel. If I add 2y to minus y, I get 1y. And if I add 4 to 2, I get 6. So again, we found our solution, y is 6. How could we find the x? We'll go back and plug that y into the y that you see in either of these two equations. Then I get 3x plus 2 times 6, that's 12, is equal to 4. Minusing my 12 and dividing by 3, I get 8/3, or negative 8/3. No problem there. That's just the answer. I mean, it's a separate equation from the first one. We should expect a different answer. The 6 is a coincidence. And it's a fraction, no big deal. I mean, so we just write that down. We did all the steps. We can check our work. Then that's just going to be what our answer is. So on to the third one. The third one is not quite in the right form to do Gaussian elimination yet. We have a minus x and we have a positive 2x. I could make those match by multiplying both sides of the bottom equation by 2. If I do that, I get minus 2x plus 4y equals 6. And adding those together, we get a lot of cancellation, except I get 0 equals 11. Okay, 0 equals 11 is a nonsensical statement. We would have no solution. I'd like to show one more way of thinking about that third equation. I could solve for x, right? Or solve for either of the variables and try substituting in, the second strategy from our practice. So if I bring my 2y over, and then I get rid of the sign by multiplying by -1 on both sides, which really just means changing the order of subtraction, I get x is equal to 2y minus 3. Substituting that back into the other equation, I wind up with -6 is equal to 5. Clearly a contradiction, and so we would conclude that this system has no solution again, which we already did. I just wanted to give you another method. Okay, that's it for this video. Thank you for your patience. Have a great day and good luck with your studies. I'll see you in the next video.